So in this video, we're going to talk about voltage, power, and energy in an electric circuit. Previously, we've been talking about, in our previous video, about current, and we said that current is simply the movement of electrons. But what makes electrons move? So if an object requires physical force to move it, it also requires force to move an electron. And in particular, we're talking about electromotive force, or EMF for short. Now, EMF has other names, and sometimes we call it a voltage or potential difference. Now, let's make uh, a more clearer definition of voltage. Now, let's say we have an element here, and we label the terminals of the element as A and the other one as B. And let's say charges cross. So uh, that terminal or that element, here in particular we have positive charges entering terminal A, and it tries to cross the element towards terminal B. Now if energy is required in order to let the charges cross between the terminals, uh, that would mean that a voltage exists between terminals A and B. So that is what we mean by voltage. So if we try to cross or try to let charges cross between two terminals, and it requires some energy, that means a voltage exists between those terminals. Now, how much voltage is uh, is there? So if let's say it requires 1 joule to cross 1 coulomb of charges, or positive charges in this case, that would mean that there exists a voltage of 1 volt between those terminals, and that 1 volt is actually just a ratio of the energy required, which in this case is 1 joule, uh, and 1 coulomb of charge. So that is the a more clearer definition of voltage and what do we mean by 1 volt. Now, a voltage, uh, in a voltage, uh, it requires polarity between the terminals, and if let's say upon the charges crossing between the terminals, in the process the element gains energy, it is said that terminal A is more positive than terminal B. So A here is more positive than B. If, however, the element loses energy in the process of transferring those charges between the terminals, it is said that the terminal A is less positive than terminal B. Or another way of saying it is terminal B is more positive than terminal A. A more formal definition of voltage is stated here from the book of Alexander and Sadiko. We have voltage as the energy required to move a unit charge through an element. From the book of Dorf and Svoboda, voltage across an element. So the term or the word across there is very important because voltage is always measured across an element. So is the work required to move a unit positive charge from the negative terminal to the positive terminal. Okay, so that is the definition. A more formal, those are the formal definitions of a voltage. So how do we label the voltage across an element? So let's say we have an element here shown on the left. Uh, to show the voltage across the element, it is always necessary to label the terminal. So let's say this is terminal X and this one is terminal Y. To show the voltage across the element, we may write voltage with a subscript XY, denoting the voltage. That voltage is between X and Y. Also, it is necessary to show the polarity of the voltage. Now, in some elements, it is not obvious where is the positive and where is the negative. For battery or elements that are sources, the battery, it is obvious where is the positive there and where is the negative. But in most cases, it is not yet obvious or defined where is positive and where is the negative. But in labeling the voltage across the element, it is always necessary to show where is the positive and where is the negative. So let's say in this illustration, we assume X to be more positive than Y. And let's say that upon measuring or computing for the voltage across the element, it showed that we got here a positive 10 volts. Okay, so if we measure positive 10 volts here, or we computed a positive 10 volts, that confirms our labeling of the polarity. So if we get positive 10 volt, that means really that our label here is correct, and terminal X is more positive than terminal Y. If, however, we got a negative 10 volts, that would mean that our initial labeling of the polarity is reversed. So in this case, if we get negative 10 volts, that would mean that X here is more positive compared to Y. Okay, and that is shown here on the left side. So there is an element and it is labeled A and B, and shown here is that the voltage is 9 volts, positive 9 volts. So that would mean that uh, terminal A is really more positive than terminal B. Now there is another equivalent uh, labeling for this, and that is shown on the immediate right. If we label A as negative and B as positive, but we change the sign of the voltage from positive 9 volts to negative 9 volts, this is also acceptable. What we mean by this is that this labeling here is equivalent to this figure. So there are two ways of labeling the voltage across an element as shown here. So that's it. If you label the voltage or you want to show the voltage across an element, it is always necessary to label the terminals and show the initial polarity of those terminals, and write the voltage as V, for example, with a subscript that is indicative of the labels of those terminals. So in this case, for this drawing, we have V sub XY. So as earlier explained, voltage was defined as the work required to move a charge between the terminals of an element. Now for variable voltage, we normally use lower cases for the quantities, and for fixed voltage, we use upper cases. So let's have an example here. So let's say we want to move uh, a charge from point A to point B. So that is what is shown here in this example. So we have an element. So that element has terminals. And let's say we label the terminal. Let's say this is A and this is B. And in A, uh, we move 6 coulomb of charge. And as the problem says, uh, um, negative 30 joules is required to move a 6 coulomb charge. Now, negative 30 here means that the element is actually losing energy. So, well, that is 30 joules of energy. And so, therefore, when we compute for the voltage across A and B, that would be negative 30 divided by 6 coulombs, and that will give us negative 5 volts. So therefore, we can conclude that terminal A here is less negative than B, or B is more positive than A. Now on the second condition, we let a negative 3 coulombs pass through the element or move through the element, and according to the computation, that will yield positive 10 volts. So in that case, that would mean that the element is actually receiving the 30 joules. And that means that terminal A is more positive than terminal B. Let's talk about power. We know that power is the time rate of expending or absorbing energy measured in joules per second or in watts. Um, let's say I am going to multiply, so shown here is the elements, and the voltage across the element is shown here as B, and current is entering the element. So current I is entering the element. Now let's say I'm going to multiply V, the voltage, and the current. So let's see what will happen. So we know V, we know that the unit of this is joules per coulomb, and we multiply this by I, and we know the unit to be coulombs per second. Uh, so in that case, that will cancel out the coulombs, leaving us with joules per second, which is actually a unit of power. So that will actually give us power for the element. Now power is measured the unit for power is the joules per second, and 1 joules per second is actually equals to 1 watt. Okay. Now, power can either be absorbed or supplied by an element. Now, how do we know that it is absorbing power or energy or supplying power or energy? Now, if let- for our element, let's say we label the voltage in this manner, so this is the positive, this is the negative, and current enters the positive terminal of the element, that would mean that the element is actually absorbing power, so it's gaining power. On the other hand, if current is leaving the positive terminal or entering the negative terminal, that would mean that the element is actually supplying power. So here the element is absorbing and here it is supplying. So this concept can be compared with, let's say you have a bank account and money is flowing towards your account. That would mean that is a positive for your account, right? And if money is flowing out, that would mean that you're losing money or you're supplying money. So that is the analogy there when it comes to whether power is being absorbed or supplied. We know power to be the rate of energy usage, and in order to get the total energy, we simply do the integration here. So to get W, for example, we need to integrate from one point in time to another point in time to get the total energy given the power. Now, since power is, as defined previously, to be the product of the voltage across an element and the current to the element, we may write energy as this one. So let's have another example. Let's say we have a battery. Now a battery has a specific polarity, and let's say this is 1.5 volts, and this battery is connected to a lamp. So here this is the lamp, and it can deliver, according to the problem, 90 milliamperes for 12 hours. So the first question is how much charge can it release? So since amps is simply the amount of charge per second, to answer the first question, all we need to do is multiply the current with the number of seconds. So that will give us this answer for the total charge that can be released. Now for the second question, since the voltage is already given, so the voltage is 1.5 volts, to get the total energy that the battery can deliver, we simply first multiply the voltage with the current and the amount of time that we use the flashlight. So that will give us this much energy that can be delivered by the battery in 12 hours. Let's have another example, and in this example there is a device and the current is entering the device, given by this expression. And also the voltage across the device is given by this expression. So the voltage is uh, proportional to the time rate of change of the current, di dt. So the question is how much charge is delivered to the device from t equals 0 to t equals 2 seconds. So how much charge delivered in 2 seconds? The second question, how much power is being absorbed by the device? And the total energy absorbed in 3 seconds. So this is the solution. So we have the device and current is entering the device uh, given by this expression, and the voltage is also given with the polarity indicated. So as you can see, the current is actually varying uh, from a maximum value of 6, and it goes down to 0 as t approaches infinity. So to answer the questions, so for Q, since we're given the current, all we need to do is apply integration from 0 to 2 seconds. So that will give us a total charge going to the device of 2.9 millicoulombs. Now, to get the power on the device, first we need to know what is the voltage across the device. So that will be 10 times the derivative of the current. So that will give us this one. Now take note that this gave us a negative number, so that will simply mean that the actual polarity is that the negative is really here and the positive is here. Okay, so that will give us a millivolt unit. Now to get power, all we need to do is multiply the current entering the device and the voltage across the device, and that will give us negative 720. So since the power here shows to be a negative number, that would mean that the device is actually supplying power. So the device is not gaining any power, but in fact it is supplying power to the outside. So to get the total energy on the device, all we need to do is again apply integration from 0 to 3 seconds, and that will give us negative 180 microjoules. So again, since power is supplied by the device, that should give us a negative energy. So, so as a comparison, voltage should be something like this one. So it starts negative 120 millivolts and approaches 0 as t approaches infinity. For power, the graph would look something like this. So it's much quicker to approach 0 because of the fourth power here. So it starts at negative 720 and approaches 0 again as t approaches infinity. So the area here, so this is power, is what is the energy here, which is a negative area. So therefore we got a negative energy. In this last example, this is an illustration of the power in a closed electrical circuit. So the total power that let's say we sum up all the power that is either absorbed or supplied by these elements. In a closed system, we have what we call conservation of power. So if we sum up all the power for each of the elements, we should get a 0. Okay, so for this example, we are asked to find the power for element number 3, and all we need to do is apply conservation of power. So we sum it up and we equate it to 0 and then compute for the power for element number 3. We yielded a positive number, so this means that uh, element 3 is actually absorbing power. And again, take note that for those elements that are shown to be negative, that means they are actually supplying power. So that's it for this video, and for our next video, we're going to discuss the linearity of an electric circuit, where it has two aspects: the homogeneity of the electric circuit or the element, and the additivity of an element. So we'll discuss that on the next video.